Chapter 8 Non-Electrolyte Solutions. Section 8.4 Pressure Composition Phase Diagram. In the ideal solution that contains liquids 1 and 2, the total vapor pressure above the surface of this solution is P total. P total equals P1 plus P2. They are the partial pressures of liquids 1 and 2. Based on Raoult's law, P1 is x1 times P1 star, P2 is x2 times P2 star. x1 and x2 are the mole fractions of liquids 1 and 2 in the solution. P1 star is the pressure of pure 1. P2 star is the pressure of pure liquid 2. Again, P total is x1 P1 star plus x2 P2 star. x2 is equal to 1 minus x1. Therefore, we can express P total as a linear function of x1 with a slope of P1 star minus P2 star. Of course, P total can also be expressed as a linear equation of x2. x1 and x2 again are mole fractions of liquids 1 and 2 in the solution. When x1 is 0, x2 is 1. Then P total is P2 star. Just by looking at this, plugging 0 here, P total is P2 star. That makes sense because we have pure liquid 2 in this case. When x1 is 1, x2 is 0, we have pure liquid 1. So P total should be P1 star. Also, you can plug in x1 equals 1 here, and then you'll get P1 star. P total is clearly a linear function of x1 as expressed. It can also be expressed as a linear function of x2. We can define y1 and y2 as the mole fraction of these two species in the gas phase as opposed to x used for the liquid phase. So y1 is P1 over P total, y2 is P2 over P total. We're going to use Raoult's law. P1 is x1 P1 star, P2 is x2 P2 star. Now let's divide y1 by P1 star, divide y2 by P2 star, and then sum it up. y1 over P1 star is x1 over P total over here, and y2 over P2 star is x2 over P total. We can combine this because they share the same denominator, and x1 plus x2 is just 1. Now we can plug in y1 equals 0. When y1 is 0, we have y2, which is 1. 1 over P2 star is 1 over P total. So P total is P2 star. When y1 is 1, you put 1 here, y2 becomes 0, and then P total is P1 star. And that makes sense, because when y1 is 1, well, it indicates we have only species 1 in the system, and therefore P total is P1 star. Now if you look at this equation, P total is no longer a linear function of y1 or a linear function of y2 as in here. So P total is indeed a linear function of the mole fraction of species 1 in the solution. It's also a linear function of x2. That's the mole fraction of species 2 in the solution. However, P total is not a linear function of y1 or y2. Instead, 1 over P total is a linear function of y1, and also it can be expressed as a linear function of y2. Again, y1 plus y2 equals 1, so you can replace y1 with 1 minus y2. Also, you can replace y2 with 1 minus y1. Now let's look at our first pressure composition phase diagram. In this diagram, we mix benzene and toluene. So in the liquid phase, we have both benzene and toluene. In the gas phase, we have benzene vapor and toluene vapor. Now let's look at this horizontal axis. What does this mean? This actually means benzene composition. But I didn't say it's a liquid phase or a gas phase or even a mixture, because if you look at this phase diagram, it's interesting. Above this black line, so there's a straight black line above this, you have higher pressure under higher pressure, we have liquid only. So we have liquid benzene and liquid toluene. Below this red curvy line, we have low pressure and we have vapor only. And in between, then we have a significant liquid phase and also a significant gas phase. I'm using V to denote vapor or gas phase. Now let's look at the horizontal mole fractions. If you can see, you have 0 to 1, and this is benzene composition. That means we have no benzene here, or toluene, and over here we have 100% benzene and no toluene. Now let's look at this line, this black line. Above this black line, we have liquid phase. So the mole fraction over here is the mole fraction of the liquid phase. What if we have the area? Look at the area below the red curvy line. We have only vapor. So those mole fractions are actually the mole fractions in the gas phase, denoted by Y. So over here you have X, over here you have Y. What if we're looking at this area in the middle? It looks like a new moon. We have both liquid phase and the gas phase. And now we need another symbol, Z. Z stands for the mole fraction of the species in both liquid and gas phases. And when there's only liquid phase, then Z1 is X1, Z2 is X2. When there's only gas phase over here, then Z1 is Y1, Z2 is Y2. Alright? But what if you have both the liquid phase and gas phase? Well, it's simple. You can look at the total number of moles of these two components in both the liquid and gas phases, and then sum it up. You get a total number of moles, N. Alright, and then you have the total number of moles of benzene in the gas phase and in the liquid phase. Alright, and then you can get a mole fraction for benzene, which is the number of moles of benzene in gas phase plus the number of moles of benzene in the liquid phase, and then divided by just the total number of moles of both components in both phases. And that's the definition of Z. Alright, Z is the mole fraction of the species overall, considering both the liquid phase and the gas phase. Alright, again, I just want to emphasize, when you have high pressure, the phase with lower volume is favored. In this case, it's the liquid phase. When you have a low pressure, the phase with lower molar volume is favored. In this case, it's gas phase. In between, you have both liquid phase and gas phase. Now let's look at this phase diagram again. This is again pressure composition phase diagram of two components. We have benzene and toluene. In the liquid phase over here, they're also in the gas phase over here, and it's possible for the liquid phase and the gas phase coexist in this area in the middle. Alright, new moon shape. And now we have a bubble point curve, which is rather straight. This is a bubble point curve. And over here we have a dew point curve, which is definitely curvy, the red one. And now we can look at the phase diagram by focusing on just one data point right here. Alright, let's look at this data point B. Here, letter B denotes binary. That means we have both the liquid and the gas phase, binary. Now we have a data point V, which denotes vapor. A data point L, which denotes liquid. So over here, at this point L, we have only the liquid phase. At point V, we have only the gas phase. At point B, well, we have both the liquid phase and the gas phase. Now we're going to prove an important rule. It's called lever rule for the binary solution. It says BV over LB. That's the ratio between this segment BV, okay, and LB, this segment, is equal to, well, the total number of moles in the liquid phase divided by the total number of moles of the gas phase. Alright, when I say total, that means over here on top, it's the number of moles of benzene plus the number of moles of toluene in the liquid phase. In the bottom, it's just again the number of moles of benzene plus the number of moles of toluene. Now in the gas phase, all right, we can prove this. How do we prove this? We need to understand what does this L, B, and V stand for. Horizontally, they are just mole fractions, but they are different mole fractions. L will give you the mole fraction of benzene in the liquid phase. V gives you the mole fraction of benzene in the gas phase. And B is the mole fraction of benzene when both liquid and gas phase coexist. You can notice this V is greater than this L. This V is more than 0.5. This L is less than 0.3. It's just because compare benzene and toluene. Benzene has a lower boiling point and a higher vapor pressure. So therefore, in the gas phase, you will find more benzene than in the liquid phase. That's why in the gas phase, the mole fraction of benzene is higher than the mole fraction of benzene in the liquid phase. B is in the middle. Now let's look at this equation. I'm going to talk about the physical meaning of this equation. First, B is the mole fraction of benzene overall. So we have the total number of moles of both benzene and toluene in both phases. So that's really the total number of moles multiplied by B. What's the physical meaning of the left hand side? Well, it's just the number of moles of benzene in the system. Okay, this is number of moles of benzene in the system, including the liquid phase and the gas phase. Alright, now let's focus on the liquid phase. In the liquid phase, how much benzene do we have? That's the number of moles of liquid times the mole fraction of benzene in the liquid. Alright, that's the physical meaning of this. The physical meaning of this part is the total number of moles in the gas phase multiplied by the mole fraction of benzene in the gas phase. So see, the left equals right because they are both the total number of moles of benzene in the system. It's just on the left we have everything included, alright, and on the right we have two separate terms. One is the number of moles of benzene in the liquid phase, the other is the number of moles of benzene in the gas phase. We can reorganize this equation. We can somehow put N liquid on the left hand side, N vap on the right hand side. We get this equation. Alright, and then B minus L. Isn't that just the segment LB? The segment LB is just B, this B minus L. V minus B is the segment BV. So we have this equation. And then we can reorganize this equation again. So BV divided by LB, so both sides divided by LB, is equal to this N liquid over N vapor. Alright, so from here to here, it's just very simple algebra. This is very simple algebra. We have just proved this lever rule for a binary solution. So now you can see this BV over LB is liquid over gas phase. Alright, so if you have a much longer BV than LB, that means you have more liquid, more amount in the liquid phase than in the gas phase. Alright, so what if this B is kind of really close to L? So let's say B goes here. When it's really close to L, that means BL is small, BV is large, and then this is large. That means mostly it's liquid. Alright, if B is closer to L, that means at point B, mostly we have the liquid phase and very little gas phase. If B is close to this V, that means we have a lot of gas phase, very little liquid phase. Now let's look at one numerical example problem, 8.4.1, of using the lever rule. Let's say we have a pressure composition phase diagram of benzene and toluene, and we know the total number of moles of benzene and toluene is 3.3 moles. So we have this equation, the number of moles of liquid benzene plus liquid toluene, and then this is the total number of moles of benzene vapor plus toluene vapor. It's 3.3 in total. And then we have the lever rule. We do this, and then we just look up the mole fraction at point B, V, and L. L, B, V. I think L is about 0.275, and B in the middle is 0.4, and V is about 0.55. Do the math, we get this ratio of 1.2. So you have two equations. One equation is this: the sum is 3.3. Another equation, the ratio is 1.2. Solve these two equations and you get these two values. The total number of moles of the liquid phase, including benzene and toluene, is 1.8 moles. The total number of moles in the gas phase, including both benzene and toluene, is 1.8 moles. Double check. 1.8 over 1.5 is indeed 1.2. 1.8 plus 1.5 is indeed 3.3. So this is a numerical example of using the level rule to predict the number of moles of these components in the liquid phase and also in the gas phase.